Good morning, everyone. My job is actually to talk about coronagraphs and maybe first and foremost connect the first two talks of the day to see why you need all this theory that Eva explained to actually do the science that Beth talked about. So this is what I tried to do today and get an understanding of how you get rid of starlight. So actually, Eva said about a career path of like maximizing distance. I think I minimized it in a way because I've moved a whole of 300 meters. Esron is located in Leiden as well. It's the Netherlands Institute for Space Research where I'm currently working, and I did my PhD and master and bachelor at Leiden University. So I just wanted to say, if you want to stay in the same area, that's also okay. It can happen. All right. So let's remind ourselves why we do it, and let's actually connect to Beth's talk first. So I think we should always ask ourselves, we're building instruments, like what's the science we're going to do and what are the science questions that we can answer? So I here have 3 science questions that I would like to start thinking about and that we are building the instrumentation to answer. It's how do planets form? Is the Earth unique? And are we alone? I think these are very fundamental questions that I am very excited to work on and build instruments for to solve them. Okay, so when you start about these science questions, I think the first thing you should do is actually Google and ask Google what it thinks. And while Google has a perfect answer for this, it's actually point your telescope to a planet. There it is. Problem solved. Yeah. So I guess it's easy, right? We're just going to answer the build a telescope and answer the questions. Turns out that if you Google the right terms, you learn about diffraction, and it doesn't hold anymore. The first thing, of course, Eva talked about this extensively, is that diffracted light from the star dominates your science image. And the flux ratios between the planets we're trying to find is actually a factor of maybe 10 million to 10 billion, which is a lot. You need to filter 10 billion photons to find the one planet photon, essentially. So we need to remove starlight to see these planets. And here's a similar curve to what Eva showed, but then for like if we have a sun at 10 parsec and we have the Earth and the Jupiter orbiting the star, what would it look like? Well, as Beth already said, like we're solving the system with a 6.5 meter telescope in space. So James Webb, if it were looking in the visible light here, it could actually resolve the system, but it doesn't see the planets because they're hidden inside this Airy pattern or the light of the star. So again, it's very important and that we get rid of this light so we can reveal these planets. And for that, actually, there are a few fundamental things that we're thinking about. And maybe it's not so obvious, but to us working in the field, it's obvious. If you want to look at a planet, you point your telescope at a star. I don't think it's obvious, but just so all you know. And this is also because we, of course, don't know where the planets are in their orbit, where they are. So we have extended objects like disks that we want to study. And also, we can actually use the optical symmetry of our telescope system and your instruments to get rid of the starlight. So point your telescope at a star. Okay, then we can think about the fundamental differences between the light of the star and the light of a planet. I think the first and most important thing is that actually they come in at a slightly different angle. And this is what we're going to use for our coronagraphs. However, the spectrum and the polarization signal of a planet is also different. So it might be good to think about ways that we can use this to our advantage. And it is usually done with post-processing. So we can measure the spectrum and then look for traces of planet spectrum, or for polarization, it's the same thing. But for now, we can't make optics that filter only certain polarization or and also get the precision that we need to find these planets. So we'll look at angle first. Now, there are a few ways to remove light that comes in under a different angle. It's actually nulling interferometry, an external occulter, and the coronagraph. I'll only be talking about the coronagraph today. Coronagraphs are optics that you have inside your instrument, which are usually like 10 millimeter or a few tenths of millimeters in size. So not something like this. Okay, so the question of today is how do we get rid of this starlight and reveal if everything's going well, like the planets, and this is actually a simulation of our solar system, how do we see these planets? Well, you use a coronagraph. And actually, maybe all of you have been a coronagraph or try to be when you want to see sun, want to see your road where you're going and you block the light in your car or with your hand. Here, I'm doing it to see the VLT in Chile. And so this is the basic principle. You block the light and you see the things next to it. And so if we define what a coronagraph does, it's actually an optical system that blocks on-axis light and transmits off-axis light. This seems simple enough. Is it simple? Well, we'll see. So maybe just the history. So a coronagraph is named after the optics used to image the solar corona. So in essence, the moon is maybe the oldest coronagraph. And so this is also why we actually built coronagraphs. So first you could only look at the corona of the sun when there was an eclipse. While traveling around is fun, but you also want to see the sun and the corona like at higher cadence for longer times. So this is why people started thinking about optics to remove the light of the sun. And Bernard Liot developed the first coronagraph to look at the sun already in 1930. And remember his name because the coronagraph he developed is now named the Liot coronagraph. And so this was used for solar physics and also for planets in our solar system. But people started also using it to look at stars. And this is an image of the Beta Pictoris disk with this coronagraph in 1984. Oh, that's too far. So I wanted to make one more assumption that Eva already alluded to, is that if we look at coronagraphs, maybe it's easy to first look at a simple clear pupil because the Fourier theory is all nice and we can think about it and without many complications. And so it's simple, rotationally symmetric. So we might even do a 1D simulation or a 1D optimization. It's ideal for coronagraphy and you just need an off-axis telescope. Now, remember that many of the telescopes we built today are not off-axis, but maybe habitable, so it likely will be. So then let's look at our high contrast imaging instrument. I define here 4 planes, A, B, C, D, that are the principal planes that we use to change the light or apodize it, so purposely changing the input of our intensity profile to see this planet. And so these are separated by Fourier math, like the Fourier transform. So we have our aperture, as Eva showed, we have our point spread function, then we have an aperture again, and then we have our point spread function. Okay, let's move the planet over and let's introduce a mask. What happens when we put in a simple dot to block the starlight? Actually, if you look at it, due to diffraction, disappointingly maybe, not a lot happens. So just putting in a mask here, you can see that the intensity of the PSF is very similar on both the science camera and the in-between intensity. So we actually did not win anything. Why? Well, if we look at our pupil plane in between, we see that there are 2 bright rings. And our pupil mask, that's after this, only blocks out 1. So a lot of the starlight is actually transmitted. We can make a smaller mask and actually block out this ring. And then we have blocked out a large part of the starlight. And we have actually made our coronagraph. You can see now that the star is much dimmer than it was before. Success. We have made a coronagraph and we can look for planets. What happens to the planet light when we do this? Actually, light comes in on a different angle. So it's, as Eva already said, it shifts in the focal plane and so it misses our mask. And so it will likely be transmitted, or at least most of it anyway. And so when we look at our pupil, we see mostly fully illuminated pupil again, like we have for the star. We block out some of it. This is important, and I'll come back to it later. But our off-axis planet is now there, and we can clearly see it. What happens when we combine both the star and planet light? Well, we've blocked out like the starlight by 2 orders of magnitude, roughly. And so we can actually see the planet light that was hidden below here. Okay, this is nice, but how well did we do? And can we do better? So for this, I will go through 5 separate performance metrics to see how well a coronagraph works. This is raw contrast. How much do we actually suppress the starlight? This is throughput, how much of the planet light is transmitted. If I make a black mask as large as the pupil, I have no light. I also have no planet light. So that's not a good coronagraph, right? So that's why what contrast is. You divide by the planet throughput. Then the next thing is inner working angle. How close to the star can you actually find planets? And the last one is robustness. We've heard from Eva that aberrations are omnipresent in our telescopes because of the atmosphere or instrument itself. We need to know how robust our coronagraphs are and how worse the performance gets when these aberrations are there. So first, raw contrast, and I might get in a fight over this within my community, but I define it this way. Raw contrast is just the normalized intensity of the residual starlight. So you can see in the orange curve here, this is a slice as Eva showed before. And we see here that on axis we have 10 to the minus 4 raw contrast, and there we have 10 to the minus 5, and it goes down. This is how I define raw contrast. However, planets are a finite size. We do want to do aperture photometry, or we want to do mesh filtering or any post-processing techniques. So it's not really useful to think about raw contrast maybe on a pixel level, but more on the diffraction size level. So we convolve it with a 2 lambda over d circular aperture or photometric aperture, and this is roughly what we get. It doesn't change much, but there we have eta s, which is just the integral over this aperture of our point spread function, the coronagraphic point spread function at a certain location where the star is located on axis. That's what this 0 means. I normalize it with the PSF, which is a non-coronagraphic PSF, just because it's easier to think about like fluxes. If we're not looking at stars with magnitudes, it's just easier to think about relative intensities because we can also multiply this with the final intensity. Now that we know what raw contrast is, let's look at planet throughput. So to remove starlight, we also did something to the pupil size, and we actually, if you go close, you actually have some of the planet light that's blocked by our mask. So it's useful to think about how much of this planet light comes through. Again, it's easy to remove all starlight, but it's difficult to do so while maximizing the throughput of the planet. And so this is when a star or a planet moves across our mask. We can see in between the LEO plane, and on the right, we can see our detector image. And we can see that the planet or the planet PSF or the post-coronagraphic PSF, it gets a little bit distorted near when it's behind the mask, but otherwise it gets transmitted quite well. And so here I took this aperture in green on the right. On the left is just what it looks like in the in-between plane right before or right after the coronagraph, the focal plane mask. And here the green circle just means our aperture. And I shifted it around to sort of mesh the maximum on this axis. And you can see that the location of where I see my planet actually distorts. And so this white dot follows the actual location here. And so if you look at it, a still image of this, we can actually see the first thing you notice, actually, the planet seems to be mostly behind our mask, but we still have light. So what is the inner working, or how close can we actually see? Well, it seems to be that we're slightly looking behind the mask. And also the location is distorted. So if you want to do astrometry, you need to think about this, or at least don't trust anything or correct for it with modeling. So here I plot the actual intensity of this PSF as function of separation. Now I don't do it for from left to right, but I do it from the start on axis to all the way to 8 lambda over d separation. You can see that there is a gradation from 0 to whatever. It's like 0.55. So we actually lose quite a bit of flux here that we remove by having this smaller LEO stop. I also plot here the perfect theoretical limit that we know and we can calculate. You can ask me about it afterwards. And you can see it's quite far off. So this might not be the best coronagraph. Now, I also want to go into contrast again, which is actually the ratio of this normalized intensity and the planet light that's transmitted. So here we have eta p, we do the same thing. We calculate at a certain location, and for a shifted PSF, we calculate the flux in a circular aperture. And then we just define the contrast as a ratio of the normalized starlight and the planet light, or the off-axis light. And contrast, or the gain in contrast, just takes into account this throughput. And just to iterate again, if you have a gain in contrast in 10, but your off-axis throughput is 1 in 10, you don't gain anything. So you should not have put in the coronagraph. Then there is the inner working angle. How close can you look at the star and still see signal? We usually define the inner working angle as where the light is 50% of the maximum for this coronagraph. Of course, this is a little bit arbitrary because there is still light coming through here in this region. Let's go back. So there's still light coming through in this region. So if you have a very bright star or off-axis planet, you could still see it. But our inner working angle, just to be consistent, we'll define it in this way. Now, this, as I said, this inner working angle is a bit arbitrary as well, because you might have coronagraphs which have a different slope in their throughput. So they might have more flux coming in here and maximize to the same intensity, and then they have the same inner working angle. But does that mean they have the same performance? Does it mean we can actually see the same planets, or are they better? So this local slope is important. And why this local slope is also important is because when there are aberrations like tip tilt, it's quicker. Like a lot more light might leak through here because of these aberrations. So this is robustness. How robust are you against aberrations? And so to show this, I have actually simulated two LEO masks. One is small, one is large, and I put in some aberrations, the Zernike modes that Eva talked about. You can see on the bottom here, this is post-coronagraphic, that this flux is much higher than this. So the more aggressive you make your coronagraph, the more sensitive you are to aberrations. So this is a fundamental trade-off. Like, how well can you control your aberrations? How aggressive can you look for planets nearby? So these are the 5 performance metrics that we can use to see how well coronagraphs are working. And so these are the ones we can use to compare performance. Can we actually change the LEO coronagraph, like the one I show here, to make it better? Well, actually, there's not much to be done. So we can change the spot size or the diameter here, but there will always be diffraction from this point. And this diffraction, we cannot remove by having only these 2 planes. So a perfect null is not achievable, at least with only these parameters. If you know why, you can look up Babinet's principle. So how do we make better coronagraphs? Well, we can modify the phase or the amplitude in our chronograph system in the multiple planes that I showed, where amplitude is really just removing light so that the residuals interfere, for example, destructively, or I just use it to block certain bright areas. And phase apodization is really where you change the phase, so you rotate your electric field vector, and then you can destructively interfere it as well. Now, if you rotate it to be this here, you can see that light can have an amplitude of -1. So to say, so this might mean that we can actually, instead of making it 0, we might actually have a more efficient way of then phase might be more efficient than amplitude. Now we will look at that in a second. Now I want to go through the different planes and for you to understand what's going on when we change the phase or the amplitude in certain planes. So let's look at plane A, the pupil plane first. And we need to realize that when we change the pupil plane, we actually change both the star and the planet light at the same time in the same way. This is because they per definition overlap here in the pupil plane. So it's nice to work in the pupil plane because actually the beam is quite large compared to the focal plane, and it's easier to manufacture masks. But because we're doing both, apodizing both the star and the planet light, we do need to do something different. And so what we like to do is actually make a region where it's dark. And so here 2 coronagraphs come in. It's called a shaped pupil coronagraph or the apodized faceplate, APP and SPC. And they do just that, only phase or only amplitude apodization. Now, because of Fourier theory, we can only make a two-sided dark zone with the amplitude, and we can make a one-sided dark hole like you see here and here with phase. And we can actually directly compare the intensities for the same side of dark hole. So this is work done by Emile Poor, where he showed that if you have the same dark hole and same parameters, you can actually have much more light being transmitted by the phase pattern than by the amplitude pattern. Although this is a very extreme case, usually it's only a slight change. What we need to realize is actually this is nice in theory, but phase is chromatic. Optical path length differences depend on your wavelength, or at least the phase that you induce is then wavelength dependent. So it might actually be easier to make amplitude masks, while and then the phase masks, despite theory saying that it might be a better coronagraph. Now here I made a phase, an apodizing phase plate. And one thing I want to leave you with, and you can think about during the breaks, is how do we define the inner working angle and the throughput if you're just moving the star around. So here I do the same thing as I did for the other focal plane coronagraphs, moving it around, and you can see there's no change in intensity. I just shift the PSF. Okay. Okay, I'll try to be close. Okay, I'll just keep it closer. Sorry. Okay, so can we apodize? So then to the focal plane, can we actually apodize the star and the planet, where this is the plane where we can apodize the star and the planet separately, like we saw for the LEO plane, LEO mask here. And the goal is here to diffract the light out of the beam like you saw here. And the first thing we can do, of course, is then change our amplitude mask to a phase mask and ask ourselves, is this more efficient? So this is now a Roget and Roget mask, a Roget and Roget coronagraph, where it's actually more efficient because we have this amplitude of -1. And but it's still not an optimal coronagraph, and it's still chromatic. So let's look at one of these coronagraphs that is mostly almost close to optimal. It's a Vortex coronagraph, and you'll play with this, I think, in the hands-on session later today. Here we have an azimuthal phase change going from 0 to 2 pi twice, because the charge here is 2, which is the amount of times the phase goes through 0. And even charges deliver optimal performance, so actually have perfect stellar rejection. And then the proof of this, actually, you can see in Dimitri Mauet's paper in Appendix C. It's actually interesting. So if you want, you can look it up. And so what happens here is when mask is diffracted, it gets, so this is the point spread function, this is the phase in the focal plane, it gets this ramp. And then here in the pupil plane, we see that it's completely dark. So actually it's blocked by the LEO stop. So there's no light here and there's no light here. So actually the Vortex is a very nice coronagraph. Now onto throughput, because of course there are more ways of measuring the performance. So here we change this charge. Look how many times it goes from 0 to 2 pi, from 2, 4, 6, and 8. And this is work done by Gareth Ruane, where we simulated the throughput. And so you can see it's actually getting closer to this theoretical curve that I showed before. And with very high throughput. But depending on the charge, the throughput changes as function of separation. Moreover, if we look at a charge 4 mask, for example, we see that there are many aberrations. So this is how much aberrations you put in. So this is very little, this is a lot. How much does my contrast change? And actually for certain modes, which are Zernike modes, we can see that even if we put like a picometer in for visible light, we already see that the light, the contrast ratio starts exceeding our 10 to the minus 10 contrast ratio. If we increase the charge, there are certain more and more modes that we actually have, you need more larger aberrations for before it starts degrading the contrast. So higher charge, less aggressive, larger in the working angle, means more robust against aberrations. And this is a general trade-off for all coronagraphs. I also want to look at stellar diameter, because it's going to be important. If we build larger and larger telescopes, more and more of our nearby stars are resolved. And And of course, resolving the system itself is nice because we can actually see Earth-like planets in the habitable zone. But if we also resolve the star and the coronagraph starts degrading, we don't gain anything. So this is why robustness against angular size of the star is important. And we see here that for charge 2, 4, 6, and 8, you have a different sensitivity curve. So this needs to be taken into account in our simulations as well. Now here, I finally go into the chromaticity of these phase masks. So here, if we change the phase of these vortex masks only a little bit, so we increase, for example, the wavelength, so the optical path length is the same, but divided by the wavelength, it will change a little bit. We can see that our coronagraph starts to perform worse and worse. And actually, the peak intensity starts to go from, well, 10 to the minus 11 all the way to 10 to the minus 4, 3, 2, 1. So we don't have a good coronagraph anymore. So we have this nice coronagraph, but in reality, if we want to observe any photons over any bandwidth, we need to think of something to make this chromaticity, the impact of chromaticity less. Now, many smart people are working on this. This can either be by changing the pattern itself, by changing the way we manufacture it, or even the material that we use to make the mask, like with meta surfaces, using classical phase, or we can use vector vortex coronagraphs, which induce achromatic phase. It's called geometric phase, by making, for example, sub-wavelength ratings here. And we can see that there are also multiple solutions. These are achromatic, so that's very nice, but you introduce different kind of chromaticity. So there's already, again, an engineering problem. And so you'll see the theory, when it gets to reality check from manufacturing, there's a big impact. And maybe the best theoretical coronagraph might not be the best coronagraph to put on a mission because we can manufacture other ones much better. Now, finally, let's introduce more complexity. So we go to an on-axis telescope. This is, of course, one of the more complex pupils that we have. This is for TMT. We can fundamentally, and this additional diffraction that's introduced by this actually fundamentally reduces the performance of our coronagraphs. They become more complex. We need to filter more light to get rid of the starlight. The way you can think of it is that it actually, all these parts of the pupil diffract additional light into nearby where we want to remove it. So you need more aberration, you need to introduce more or apodization to remove the light, and therefore the performance is lower. Now, additional complexity is that we can no longer use simple math to actually calculate everything. We need to solve everything numerically and optimize everything numerically to find the best one. But we also have been doing this for a long time because all our 8-meter class and even before telescopes have these complex pupil shapes. So we just need to deal with it. Now, what I'm going to talk about next is that there are many solutions to solve the additional diffraction and get best good performing coronagraphs. And I will use a lot of acronyms, but just keep in mind, these are just people trying to solve the problem by changing both the amplitude, the phase, only phase, or something in between. So the first thing we can do is actually look at two coronagraphs we already talked about. So this is the LEO mask. And for example, you can add a grayscale apodizer to your pupil plane and change the LEO stop a little bit. You already get you get a better performance. Another thing is you can not use grayscale. It might be difficult to manufacture. You can use binary masks. They do the same thing, just diffract the light differently to make a different point spread function for a better rejection ratio by this LEO mask. And the same is true for the ring apodized vortex coronagraph. So this is the apodized pupil LEO coronagraph. This is the ring apodized vortex coronagraph. You're already seeing that I'm starting to use a lot more acronyms. I'll come back to that in a second. But here we changed the region with a lower transmission to actually improve performance. And this will be a design that will be installed on the ELT, on the METIS instrument. Now you can also, with apodization, add more apodization with the deformable mirrors that might be in your system. So you add more complexity, you optimize these surfaces, you get more degrees of freedom, so you get better performance. This is done the PSF that you have with 10 to the minus 10 contrast for a vortex and a very complex pupil shape. So it's the DM-assisted apodized vortex coronagraph. And then we can also do different things. We can add some sort of lenses or mirrors to change the intensity shape of our beam. So it's not just a uniform pupil, but actually maybe more like a Gaussian profile. It's called the phase-induced amplitude apodization, PIA. And of course, you can then in the focal plane add amplitude mask, phase mask, or anything. And this is the PIA CMC, but you also have a PIA vortex. And well, there's much more you can do. Ultimately, there are many coronagraphs. That's my point. And this might not already be up to date. There might be more, and I might be omitting some. But the thing is, this is a complex problem. Many people have tried to solve it with different technologies, different ideas, fundamental physics. So the tree of life or the plot, it becomes much more complex. And Olivier Guillon already noticed this in 2006 and thought, well, let's compare them at least for some of the metrics to see which one are useful and which one are not. And so he tried to cut down this tree already in 2006 by comparing the off-axis throughput for all of these. And you can see some of them, for example, the apodized pupil Leo coronagraphs are here, vortex coronagraphs here, PIA here, and then the theoretical limit. So you know that none of these are close to the theoretical limit. And these are the point spread functions that he simulated to make these curves. I think his attempt was unsuccessful, but partially successful because some of these we don't see anymore, but then we made new ones. And so the problem keeps on going. So how do we deal with this? Well, the origin of this is that the telescopes are not optimized for our coronagraphs. We're not building off-axis telescopes. We're making on-axis with different segments. We're making... Oh, sorry. Oh, yeah, thanks. So it's not easy to design a coronagraph that's optimal or find the optimal coronagraph. It's also the optics, the telescope is imperfect. There's active systems. So you can do a whole lot and all different things. And so it's difficult to see what's best. And it's been in development for the last 25 years. So our theory kept improving. Our optimization techniques kept improving. Manufacturing has changed. Our fundamental like optics that we can make, how tiny scales we can use, or that's all changing. And so we need to find a way to sort of get this into some comparison to ultimately find out what are we going to do for habitable worlds. Because there will only be limited space on this mission. We can only select a few. So which one is the best for which? I mean, it also can depend on the science case, of course. So that's another complicating factor. So the ultimate thing we can do is to look for a better theoretical and fair theoretical comparison and also do a laboratory comparison. And so later this week, you will hear more about these yield calculations. You actually work on it yourself. But for the planet, these yield calculations, the coronagraph is actually many parameters that go into it because it determines most of it is the on-axis or the star rejection ratio, and this depends on many factors. So I already talked about raw contrast, planet throughput, inner working angle. Field of view is another one. Spectral bandwidth, how chromatic is it? Robustness to stellar diameter or low order aberrations. The complexity, how easy is it to manufacture the masks? How easy is it to simulate the masks? Our models need to be close to the reality as well to better do wavefront sensing and control. Can we actually integrate wavefront sensing with our mask to make the overall system perform better? And then there's also sensitivity to polarization. So it's very complex. And so we take all this, we put it in, we create a fake population of planets, we simulate the observing sequences, and then we take into account all the noises, aberrations, the coronagraph parameters. And the only question we're asking ourselves, how many planets did this mission find? And so this is a way to fairly compare all these coronagraphs with their different performances. And ultimately, we can even ask ourselves the question: Can we change the observatory or our scheduling to better match and get a higher exoplanet yield? Because the goal of habitable worlds is to find 25 Earth-like exoplanets in its mission lifetime. We can only know how many planets we find if we have the proper simulation tool and do the right trade-offs. In the lab, it's actually more complicated because then there are many different systems, many different setups that are difficult to compare. But this was actually work done by the Chronograph Design Survey team, and also Bertrand and Sonne et al. Worked on this to make a sort of at least a comparison in contrast versus angular separation. And so there are many here. You can recognize the PIA, Vortex, Leo coronagraphs, but this one here, it's actually the classical Leo coronagraph, and it's currently performing best. Maybe surprisingly, the Leo coronagraph for now is simply the best. Why is that? So its performance right now is a few times 10 to the minus 10, so it's getting actually close for finite bandwidth, getting close to what we need for habitable worlds. And for now, I think it's mostly because simple is better. You're not introducing complexity that you need to model, that you need to, where more aberrations are created from. And also, it's the system level interactions that we can actually better understand and model. However, this coronagraph still does not have a great inner working angle and maybe not the best throughput. So ultimately, we want to improve upon this. But for now, we're getting there. That's the main message. And so I would like to end this lecture with some final thoughts and some takeaways. And of course, I hope the main thing you learned today is that the coronagraph is an optical system that blocks on-axis starlight and removes off and transmits off-axis planet light. However, also that we're not there yet in terms of designs because they're not close enough yet to the theoretical limit, so we can improve the theory. Also in the laboratory, the coronagraphs do not reach their simulated performance, so we need to do work there. And this is also because the coronagraphs are part of a system which we might need to optimize as a whole to better understand the system level interactions between the coronagraph and the system it's in. And ultimately, the design space is just extremely complex. And so many parameters impact the exoplanet yield, so the end-to-end performance. And what I hope you'll have after this talk, that you're excited to see the results, that you want to participate in this effort, because we need you to realize the Habitable Worlds Observatory and to get these planets. So with that, I would like to end. Thank you.
Questions? Raise your hand. Hi. Okay, we're here. Jillian.
Hi, I had a question about your examples. Most of the examples you showed had kind of the optimal setup for a singular star, no background light when you're looking for a planet. How much more complicated does this look when you're looking at an uneven light source? For example, a close-in binary, and you're trying to look for a planet around that. And how do you deal with that to try to find a planet with a more complicated system?
Yeah, so I mean, finding a planet around a close binary is extremely difficult because you have a second bright object right next to your other bright object that you know how to deal with. And so this gets a lot more complex. And also because binaries are all different, have orbits, I would not recommend actually making a coronagraph specifically designed to do this. So you would need some sort of active system that can get additional nulls depending on where this binary is. So for now, I think like close-in binaries with a planet around it is something that you don't want to go to because we don't know. I mean, there's too many degrees of freedom. And for all the other things like aberrations, yeah. So one thing we can do for slightly larger separation binaries is do wavefront control in a way where we dig a dark hole for both stars at the same location where we expect a planet. And it's actually active research because there are a lot of binaries out there. But this is mostly in control. This is not per se what you do with your coronagraph.
Thank you.
Hi. I had two questions, if that's okay.
Sure.
So I had tough time understanding the difference between like regular amplitude and phase apodization versus DM-induced apodization. So how does a DM coming into the picture actually change how, the wavefront and everything is apodized?
Yes. So in principle, if you have only one DM that's in the pupil plane, then it doesn't matter which plane. So you apodize. The reason why you would normally not use a deformable mirror for this is because you want to use it to correct aberrations. So if you put a lot of aberrations or apodization on it, so you want to make a dark hole, then you don't have a lot of stroke or left to fix the aberrations that are in your system. So this is why you would want to use a separate mask. However, if you already have almost everything in place, then the apodization you can do with a deformable mirror is minimal. So you can actually do this. So this with the DM-assisted Vortex coronagraph. And then, I mean, at some point, the DM becomes part of the coronagraph anyway, because there are always aberrations. So you can see them in sort of one system where if you have aberrations, you need to fix them anyway to get the contrast performance. So you use your deformable mirrors to correct for it. There's no difference almost in like it does the same thing, right? You remove Starlight.
Got it. And my second question was, when you sort of described the difference between pupil plane and focal plane apodization, you mentioned how in the case of the focal plane, we changed to using the face mask or the face apodization mask. So is there a difference between how the face mask works in the pupil plane versus the focal plane, or is it pretty much the same thing except the placement is different?
Yeah, so usually we use similar technologies in the pupil plane or the focal plane. However, for the focal plane, of course, you need to make things at very small scales. So usually the size of a point spread function is microns, right? Tens of microns, depending on your optical system and the design choices. So you need to have technology that can make changes on very small scales. And for the pupil plane, this is not the case. You can do it on larger scales.
Last question over here.
Yeah.
the middle.
Hi. Thanks for the very insightful talk, David. You mentioned robustness is one of the 5 metrics of performance for a coronagraph. And I was just wondering, how would you quantify robustness? How do you, is there a unit of measurement or something? How would you quantify that?
I think usually it's just a relative. You compare coronagraphs with similar aberrations that you expect that to be realistic, and then you compare them. Yeah, I don't think that you can just quantify I mean, you can quantify the total amount of aberrations you put in and the total amount of contrast, and you can make plots of this, of course. But some coronagraphs are sensitive to different modes. So, for example, if you know your telescope has a very certain flexure mode, your main primary mirror, you might want to make a coronagraph that's optimized to be insensitive to this specific mode, because if this happens, then your coronagraph will perform better compared to the others.
Yeah, thank you.